Newton used Kepler's laws, including all other observations, and formulated his theory of universal gravity. According to this theory, every object in the universe attracts every other object with a definite force. This force is directly proportional to the product of the masses of the two objects and is inversely proportional to the square of the distance between them. Here, two objects with masses m1 and m2 are shown. The distance between these objects is d. The gravitational force of attraction between these two objects is given by F is directly proportional to the product of m1 and m2. Similarly, F is inversely proportional to d square. Combining both these equations, we get F is proportional to m1 into m2 upon d square. F is equal to g into m1 into m2 upon d square. Here, g is the constant of proportionality and is called the universal gravitational constant. From this equation, it can be seen that the value of g is the gravitational force acting between two unit masses kept at a unit distance away from each other. Thus, in SI units, the value of g is equal to the gravitational force between two masses of 1 kilogram kept 1 meter apart. G is equal to F into d square upon m1 into m2. From this equation, come, let us know the SI unit of universal gravitational constant, for which let us first write the units of force F, distance d, and mass m. Therefore, SI unit of g is equal to Newton into meter square upon kilogram into kilogram. Thus, SI unit of g is equal to Newton meter square per kilogram square. The value of g was first experimentally measured by Henry Cavendish. In SI units, the value of g is 6.673 into 10 raised to minus 11 Newton meter square per kilogram square. The value of g does not depend upon the nature and size of the objects. It also does not depend on the nature of the medium between the two objects. Therefore, it is called the universal constant of gravitation. Suppose the value of g would have been twice of its original value. Then what would have happened? What do you think? If the value of g would have been twice of 6.673 into 10 raised to minus 11 Newton meter square per kilogram square, then the gravitational force would have been doubled, provided the masses of two objects and the distance between them is constant. From the equation, F is equal to g into m1 into m2 upon d square, it is clear that if the mass of one object is doubled, the force between the two objects also doubles. Also, if the distance is doubled, the force decreases by a factor of 4. If two bodies are spherical, the direction of the force is always along the line joining the centers of the two bodies, and the distance between the centers is taken to be d. But if two bodies are not spherical or having irregular shape, then the direction of force is along the line joining their centers of mass, and d is taken to be the distance between two centers of mass. The center of mass of an object is the point inside or outside the object at which the total mass of the object can be assumed to be concentrated. The center of mass of a spherical object having uniform density is at its geometrical center. The center of mass of any object having uniform density is at its centroid. In Newton's universal law of gravitation, Newton assumed inverse square dependence on distance. He assumed this dependence due to Kepler's third law. Now you must be wondering, how did the Kepler's third law help Newton? To know this, let us first know about the magnitude of centripetal force. Consider an object moving in a circle with constant speed. We have already seen that there exists a force on the object moving in a circle which is directed towards the center of the circle. This force is called the centripetal force. If the mass of the object is denoted by m, radius of the circle is denoted by r, and its speed is denoted by v, then it can be shown that the magnitude of centripetal force is given by m into v square upon r. The magnitude of centripetal force is proved mathematically, which you will learn in higher grades. If a planet is revolving around the sun in a circular orbit in uniform circular motion, then the centripetal force acting on the planet towards the sun must be F is equal to m into v square upon r. This is equation 1. Here, m is the mass of planet, v is its speed, and r is the distance of the planet from the sun. The speed of the planet is found out using the period of evolution t. And radius r. It is found out using the formula speed is equal to distance traveled upon time taken. In this formula, distance traveled is equal to the distance traveled by the planet in one revolution, which is equal to the perimeter of the orbit, which is equal to 2 pi r. The time taken by the planet is equal to period of revolution, which is equal to t. Therefore, speed of the planet v is equal to perimeter of the orbit upon period of revolution, which is equal to 2 pi r upon t. This is equation 2. Substituting equation 2 in equation 1, we get F is equal to m into 2 pi r upon t, the bracket square upon r. Therefore, F is equal to 4m pi square r upon t square. Multiplying and dividing this equation by r square, we get, therefore, F is equal to 4m pi square upon r square into r cube upon t square. According to Kepler's third law, t square upon r cube is equal to k is equal to constant. Therefore, F is equal to 4m pi square upon r square k. But 4m pi square upon k is a constant. Thus, F is inversely proportional to r square. Thus, Newton concluded that the centripetal force acting between the sun and the planets, which is responsible for its circular motion, must be inversely proportional to the square of the distance between the planet and the sun. Newton identified this force with the force of gravity and hence postulated the inverse square law of gravitation. The gravitational force is much weaker than other forces in nature, but it controls the universe and decides its future. This is possible because of the huge masses of planets, stars, and other constituents of the universe. Come, let us understand how to calculate the gravitational force between two objects. Suppose the mass of one object is 4 kilograms and the other 5 kilograms. If the distance between them is 0.5 meter, then let us find out the gravitational force between these two objects. The gravitational force F is found out using the formula F is equal to G into m1 into m2 upon r square. Here, G is equal to 6.67 into 10 raised to minus 11 Newton meter square per kilogram square. M1 is equal to 4 kilograms. M2 is equal to 5 kilograms. R is equal to 0.5 meter. Substituting all these values, we get F is equal to 6.67 into 10 raised to minus 11 into 4 into 5 upon 0.5 square. Therefore, the gravitational force between two objects, F, is equal to 533.6 into 10 raised to minus 11 Newton. This force is very low to attract the objects towards each other. Now you must have surely understood why these two objects do not get attracted towards each other. Come, let us now solve some numerical examples based on the topics we have learned so far.